So welcome back, everybody. I just wanted to give some quick messages. So I made a small change to the program for this week, for today, because what I wanted, instead of introducing a new topic, which is about the numerical solution of homework number 5, where you're looking at the Earth-Sun problem, I was thinking of saying something about exercise 3 and 5. In particular, since many of you had forgotten a little bit about the curl and how we calculate the curl over force, because you need that in exercise 3. And then we are going to take a little look at exercise 5, which is an example of you studying the work energy theorem. And when we're done with that, I shouldn't use more than 10 minutes. Then we're just gonna work on the exercises for this specific week. So let me just bring up some of the things which we discussed on Wednesday, in particular with the calculation of the curl of the forces. So let me switch to the whiteboard here. And let's bring that up. This, by the way, is recorded, this session here, so that in case you want to revisit it, you can always look into it. So if you look back at what we did on Wednesday, one of the definitions of a conservative force is clearly that this is a necessary condition, but it's not sufficient. So that means that it conserves energy as well. Is obviously that the force depends only on the spatial degrees of freedom or position. Then the important condition then is that F is actually equal to the gradient of the potential. So in many cases, we do have a potential. You will typically start with a potential, and then you can use this relation here if the potential depends only on the spatial degrees of freedom. If there is a time dependence, this is most likely not going to be a conservative force. Energy will most likely not be conserved, linear momentum will not be conserved, and angular momentum will not be conserved. On Monday, next week, we are going to summarize many of these things, and we are going to link these conservation laws to fundamental symmetries of the interaction. So if linear momentum is conserved, that means that the interaction or the potential is translationally invariant. That's an important invariance, and we're going to define that in more detail on Monday. And it means also that if angular momentum is conserved, then the potential is what we call rotationally invariant. So if you rotate the system, the potential gives the same value. So these are important symmetries in science and physics. And actually, for those of you who are thinking a path in particle physics, so particle physics is this fantastic field where you have taken basic symmetries of the interactions, and with those, you can predict which particles should be there or not. And that's a fantastic thing if you think of our field physics, that you can actually, based on some extremely simple properties, you can make predictions about what nature is going to look like. But let's get back to the important aspects. So on Wednesday, we looked at two types of potentials. In exercise 3, what you have to do is actually repeat much of the same. So that's why we took it up. So in exercise 3, you have this guy here, Vx, y, z, and which is given by a constant a. So I should have written that in the text, that this is a constant, x squared plus c squared, divided by another constant, which we just called a squared. So these two guys here, they are just constants. So sorry for that, for having forgotten that in the exercise text. I was reminded of that last year, but I happen to have a goldfish memory, so I need to have a continuous reboot of my memory, right? Okay, so what you need to do then, the first step is actually to calculate the force. So you need the x, y, z, and that's given by the gradient of this potential. And I just write it like this. So what you would need then is like the f of x, which is given by dv d of x. And when you take the derivative, that simply gives you minus x of a divided by a squared, and then e to the minus x squared minus c squared divided by 2a squared. So that's the x direction. If you do the same thing in the y direction, you will find that this is equal to that one, to the derivative with respect to y, and you will find that that is equal to 0. So if you look at these expressions, so one thing you're being asked is linear momentum conserved? So when you look at these expressions for the forces, you can say immediately whether linear momentum is conserved or not in the x, y, and I'm not giving you the c direction because that's part of the exercise. So what could you say immediately without doing any calculations about conservation of linear momentum? Yeah?
It's not conserved in x, but it's conserved in y.
Excellent. So it's not conserved in the x direction, but it's conserved in the y direction. Now, if you want to figure out whether this is a conservative force or not, whether energy is conserved, you need to calculate the curl of this force, actually. So let me remind you of that. So what you need now to find out if energy is conserved energy or not, then we need actually to find the curl of the force. And we want to show that this one is equal to 0. So let me remind you of homework number 1, where we actually looked at the additivity of the curl. So what you guys actually did was to calculate the cross product of two vectors. And if we write it out, this would be the same as ay of bz minus az of dy multiplied with a vector in the y direction plus az of bx minus ax times bz of j plus, and then we have the final term, which is ax of by minus ay of by multiplied with k. Now you can rewrite this, and this is meant for those of you who now are studying linear algebra. So how many of you have seen a determinant? Okay, so I see many people a little bit on shaky ground, but let me mention it for those of you who probably already have fallen in love with linear algebra. Linear algebra is a beautiful field, actually. So you can rewrite that in terms of a determinant where you have I of j of k, and then you have ax, ay, and az, and you have b of x, b of y. So this is not meant to intimidate those of you who have not taken linear algebra. So this is just a kind of additional type of information. But what you will find out when you now look at the curl of the force is that this is going to be equal, and now you need all these nice expressions. So you would need a d of d, and this is going to be a dy, multiplied with f of z, minus a d of dz of f of y, and this is multiplied with the unit vector in the x direction. There's going to be a plus a d of x of fc minus a d dz of f of x multiplied with j plus a d of x of f of y minus a d dy of f of x multiplied with the unit vector in the c direction. So these are the equations which you need to plug in. So the gravitational force which we looked at on Monday is an object which depends on x, y, and z, and that gives a little bit more greasy expression when you're going to calculate the derivatives. you will find the answer actually in the lecture notes, by the way. But for the exercise here, exercise 3, you need to calculate this with the force you have, and then show that the curl is equal to 0. Then you can say this is a conservative force. So the first step you need in this exercise, exercise 3, is to calculate the force from the potential. So you would need the expression which you see here. That's the first thing you need to do, to find the force. And then when you found the force, the next thing you need to do is actually because the force is already something which depends only on the spatial degrees of freedom. So you can now actually, with the expression you have, you can calculate the curl. And what you will see then is that this is going to be a force which conserves energy. This expression for the cross products are expressions which you will also use when you calculate the angular momentum. And then you're going to see whether the angular momentum is conserved in the X, Y, and Z direction. So these kind of steps we are doing now are pretty standard steps which we always use when we are studying whether potential is energy, leads to energy conservation, momentum conservation, or angular momentum conservation. And you will encounter this way of reasoning in basically all physics courses. When you do quantum mechanics, you're going to encounter this kind of argument. When you do electromagnetism, you're going to do that. If you do general relativity, it's the same, over again, over and over again. So having seen it now, just keep in mind that this is something you will encounter again and again in physics. Any questions to exercise 3? Something which is unclear. Now, the other exercise I wanted to say something about is exercise number 5, because that's a kind of exercise where you have to think a little bit more, and it's an exercise which deals with the work energy theorem. So let me just give you some hints about the exercise. So in exercise 5, what we have is a velocity which is given like a parameter alpha divided by x. Now, nothing else is said here, right? Except that you can assume that you have a force which depends only on the spatial degrees of freedom. So we need to make some assumptions. So we assume now, and this is how we can use the work energy theorem, F is equal to f of x. So we are still living in one dimension. Then we could say, so this means that energy is also assumed to be conserved. So we can also assume that the curl, since this is also living in one dimension only, this is equal to 0. What we know then, so we could define that energy at time t equals 0 is equal to E0. And we know that energy is conserved. So that means that at a later time, or in another position, this is going to be given by a potential V of x plus 1/2 times mass. And then we have the velocity squared. And the velocity squared is alpha divided by x squared. Now, what I can say next is that, okay, let me try to find the potential. So one thing I can do now is to take the derivative with respect to x. Now, what I know, so these are kind of tricks which you will encounter again and again. So sometimes it can be difficult to actually find the right way to approach a problem like this. So we know that E0 is a constant, right? So if I take the derivative of d of E0 with respect to x, this is just a constant. This is equal to 0. And this is equal to dv of d of x. And then I have the kinetic energy term, which depends on x. So I get a factor of 2 and a factor of minus. So I get alpha squared divided by x cubed. So why did I do that? We want to find the force, right? And we know that the force is the derivative of the potential with respect to x, right? So this is the reason why I now take the derivative of the expression for the energy with respect to position. Okay? So we know that this quantity which you see here is minus f of x. So that means that f of x now is equal to minus m of alpha squared divided by x cubed. So we found an expression for the force because we had the work energy theorem. And from that, we can simply now say that, okay, I know if I take the derivative of the potential with respect to x, that is equal to the force. So these are the kind of small tricks you need to think of if you want to use the work energy theorem to find specific quantities. If somebody has just given you the velocity, just to give an example. So these are the kind of manipulations which sometimes it takes some time to get started and find the right way to attack the problem. If you then look at one of the other exercises, then we have given a force, which now has an additional term, and then we want to find the potential energy. So with a given force, this is a little bit later in the exercise, given f of x, find v of x. Then we know, now we're going to do the following. We know that the work energy theorem says that v of x minus v of x0 is equal to minus x0 up to x, and then f of x prime of v of x prime. Okay? So if I now want to simplify life, what kind of value could I give to x0 if I want to calculate here?
0.
0, excellent. So we would just put that one to 0. Now, v of x0, so remember now that what you always end up calculating are energy differences. So we can define a scale. So we could now, again, since we were so ambitious with x0 equal to 0, we could now give a value to v of x0, right? So what could we use as a value? Again, 0. Excellent. Or you could just put it to a constant, right? Then you would just have to carry a constant with you. So remember now that when you look at energies, they're always related to some specific scale. And we've chosen x0 as a scale, which is a convenient scale in order to run calculations. So that means that we would also put v of x0 equal to 0. And now we can integrate. So if we integrate the force which we have, then we find that v of x0 is going to be equal to k of x squared divided by 2 minus k of x to the power of 4 divided by 4 divided by alpha squared. Now, one thing I wanted to do now is just to switch from that and make a plot. So in this exercise, which you have, we want you to make the plot of the potential and then use the relation between kinetic energy and potential energy to say something about velocities, right? So this is where we want to use you to use your intuition about what kind of physics do you expect when you plot the potential? So what kind of motion would you expect here? And this is a kind of exercise which we are going to do again and again and again and again. And that's why it's so useful if you can plot a potential. If it conserves energy, you have kinetic energy and potential energy, and you can always look at the interplay between potential and kinetic energies. So if you can plot it in one dimension, for instance, you can easily say something about what kind of physics you expect in different points in space. So let me bring up the plot of the potential. So I have a, let me just take that one away. Can I take this away? Is that okay with everybody? So let me just bring up the plot of the potential. So I made a plot here. So if you look at that one, it looks like this. So this is the closest you get to my life, actually. So when I was a student and I escaped, oops, it didn't, let me just bring back the right one here. Here we are. So when I escaped home, I went to university, I was down here, right? I was living in something like this. And then suddenly I got a little bit more ambitious and I got a little bit more energy. And I was able to perhaps get a little bit higher up, right? So the kind of way you should think of this potential now is what kind of energy you would expect here. And you see you have zero potential energy, right? So it means that if you start up here, you have some kinetic energy. So I got some kicks and a lot of inputs from all the friends I met at university, and that kicked me above the brink. And since then, I've been a kind of person in free fall. Jokes apart, this is the kind of things you would make with plots, and then you can always try to reason. What is the potential energy? What is the kinetic energy? How much energy, or how big a velocity would you need to get up here and to escape from the potential? If you're doing quantum physics, this is often a thing you would do when you're tailoring potentials, because you want to trap particles in a potential, and then you want to avoid them to escape. So you have to design a potential in a specific way. And this kind of way of thinking is actually one of the fundamental ways we often think, if we have the potential energy. Okay, that was enough from my side. I'm going to stop the recording now, and then we are going to solve exercises. So Julie and I will float around in the room here, and George is going to be with the people online. I'm just going to stop the recording, and then we are just going to start doing things here. So for those of you online, George will now be the one who is going to take care of you, and Julie and I will just be discussing with people here. I'm going to stop the recording. The recording will be saved.